In the last couple of videos, we looked at the idea of power functions. Now today we're going to start looking at radical functions. The word radical comes from the Latin word radix, which means root. So these are root functions. So we're going to look, first of all, what if we have an even root? If we have an even root, then the graph is always going to start at 0, 0, and is going to curve up and out. Now that does keep going up infinitely, even though it looks like maybe it would flatten out at some time. No, it doesn't ever flatten out. It just keeps going up. So we're going to once again look at and analyze the properties of the graph based on what we see there. So we see that the domain and range are both 0 to infinity, inclusive. The x and y intercepts are both 0. It's continuous over its domain because I can draw that whole thing without picking up my pencil or writing utensil. There's no symmetry. It's increasing. Now notice a little difference here between the continuity and the increasing. The continuity includes the 0. The increasing does not. Increasing and decreasing never include the end point of an interval. Extrema, it has an absolute minimum at 0, 0. That's the lowest it's ever going to go down. And end behavior, the limit as x goes to infinity is infinity. There is no limit as x goes to negative infinity since the graph doesn't go over to the left there. Likewise, if we have here the odd root, the nth root, so the difference here is we still have this part here, looks pretty much the same, but now because we can take an odd root of a negative number, we have this part going off to the left also. So now our domain and range become negative infinity to infinity. X and y intercepts are both still 0. It's continuous over all real numbers. And symmetric through the origin. Remember that symmetric through the origin, once again, means that f of negative x equals negative f of x. So you can test that out pretty easily. It's increasing over its whole domain, from negative infinity to infinity. No extrema because it keeps going up infinitely to the right and down infinitely to the left, and doesn't have any places where it flattens out there. End behavior, now we do have limits at both ends, so as x goes to negative infinity, the function is going to negative infinity, and as x goes to infinity, the whole thing is going to infinity. So we're going to take and look at some variations on that as we look at determining all these properties of some different radical functions. So we want to graph and analyze f of x equals 5 times the square root of 2x cubed. So we see that there are a couple of things that are going to affect this graph, the 5 and the 2 there. The 5, if we talk about our transformations, the 5 is an a value. So that's taking all of the a's and stretching them. And the 2, well, the 2 is a little troublesome because we kind of have this square root going on, and then we have the cube. So we have two different things going on there. So the key thing here is that x cubed isn't really going to have much effect here. The 2 and the 5 we're not really going to worry about too much. We have an even root, so we know we can't take an even root of a negative number. So the graph, we're not going to get too caught up in the graphs right now. We can do more with those later. Is still going to be this kind of thing. It's not shifted left or right. So that's a big important thing. It may be kind of like that. It may be slightly different. It may look more like this. And the reason for that is because of this x cubed, that the power is higher than the root. So that means it's going to go up faster. But in terms of looking at our domain and range and all of these things, that's not going to have any effect on it. So they have given us a table here with some values that we could look at that a little more closely. But that's going to be good enough. So let's look at domain. It is going to be from 0 to infinity. The range is going to be from 0 to infinity also. We want the intercepts. X and Y intercepts are both 0, 0. The end behavior, nothing to the left, so we look to the right. The limit as x goes to infinity of this function is infinity. Now notice, whether I'm looking at the red graph here or the blue, it doesn't make any difference to any of these things. Continuity, likewise, it's continuous over its domain, which is continuous from 0 to infinity. We make that one small change there on the domain, and we don't include the 0 there. And where is it? Sorry, we do include the 0 on that one. It's the increasing, decreasing, where we don't include that. 0 to infinity, it's continuous, and it's increasing over its whole domain. So increasing from 0 to infinity. So for this, a key thing was, I don't know, I don't really care too much whether it's the blue or the red. That's minor detail, but I know with either one, I cannot go to the left of the x-axis because I am taking the square root of whatever is inside of here, so I can't have a negative inside of that function. With this next one, we have a little bit more complex function here. We want to look carefully at what's going on with this and see what's really going to affect the things that we're interested in finding: domain, range, intercepts, and so on. And what are some ways we can maybe simplify finding some of those? So first, if we look at that from the standpoint of transformations, we rewrite it as f of x equals 1/2 fifth root of 3x minus 4 thirds. Remember that we always want to factor out that coefficient of x from what's inside of here. So we see from that we have an a value of 1/2, a b value of 3, and an h value of 4 thirds. So that's going to help us a little bit in graphing. Let's get a few points here to help us see just where that's going to be. We know the parent function goes through 0, 0, 1, 1, and negative 1, negative 1. So let's look at how those are transformed. So if we apply the 1/2 first, we see that each of the y values of the 1, 1, and the 1, negative 1 are going to be cut in half. So that's going to be 1, 1/2. Now let's extend that out. We know that the parent function also contains the point 32, 2. That's not much help to us. So we're going to just leave it there. And so we'd have this point here at the negative 1, 1/2, negative 1/2. And the 3 is going to take and it's going to compress horizontally by a factor of 3. So this is getting pretty ugly for trying to graph accurately. But fortunately, that's not going to be too much of an issue for us. So it's going to move that way in here somewhere. So we're going to have 1/3, 1/2, and negative 1/3, negative 1/2. Okay, now we still have the 4 thirds there. So let's look at what happens with that. So that's going to take the whole thing and shift it to the right 4/3. Now that's pretty significant because we see that this point right here, the point that is on the origin now, is going to be shifted to the right 4/3. So it's going to be at 1 1/3 or 4/3 right there. And these other points, you know what? I don't really care too much exactly where they're going to be. Now this is going to ask us for the y-intercept. So we're going to want to find that a different way other than just looking at the transformation. So there's our very rough sketch of our function. Let's see if we can figure out these values that we need based on that. Well, our domain is nothing different than what we would expect from the fifth root. So the domain is just negative infinity to infinity, or r. Range is the same. The intercepts. Okay, well, from this, it looks like our x-intercept is 4/3. And that's just from our h value that we saw of 4/3, shifting this over to the right. So we got this point right here was 4/3, 0. Okay. Now, if we didn't remember that, how else could we find the x? Well, we could put 0 in for y. So if we put 0 in for y, we would have 0 equals 1/2 fifth root of 3x minus 4. For that whole thing to be 0, we might note that, oh, well, the only way that's going to happen is if 3x minus 4 equals 0, which is x equals 4/3. So that confirms what we got from the transformation there. So y-intercept 4/3, or x-intercept. What about y-intercept? Now, we said that one, we can't really tell from what we've done there, but it's simple enough to go back and find a y-intercept, because the y-intercept is always when x equals 0. So if we put a 0 value in for x, we have y equals 1/2 fifth root of 3 times 0 minus 4, or y equals 1/2 the fifth root of negative 4. What in the world is the fifth root of negative 4? Well, I know negative 1. And the fifth root of negative 32, oh, where am I getting negative 32? Well, because I know that 32 is the fifth power of 2. 2 to the fifth power is 32. So I know that this right here, this fifth root of negative 4, is something close to, but a little bit less than, negative 1. So what is my y-intercept? Well, it's actually just that. The fifth root of negative 4 over 2. And we see from the graph, it looks like that point is reasonably just a little bit less than our negative 1 there. That's not very accurate, but good enough. Next, we want the end behavior. So we have the limit as x goes to negative infinity. Just what we'd expect from what we've done before is negative infinity. And the limit as x approaches infinity of f of x, running out of room there on the bottom, sorry, that's not very good notation, equals infinity. Continuity, it's continuous from negative infinity to infinity, and it is always increasing. So increasing from negative infinity to infinity. Remember, when we talk about increasing, we're looking at The y values are always increasing as we move from left to right. On this last example of this type, we're looking for a little less information, just looking for what are the intercepts of this graph. And so we're going to practice what we saw in the last one, where we just plug some zeros in to find that. So for a y-intercept, we know that the x is 0. So we're going to have y equals negative cube root of 8 times 0 squared minus 4. And so that's going to give us the negative cube root of negative 4. Well, a cube root of a negative I know is negative, so we can go one step further with that and say those negatives are going to cancel each other out, and that's just the cube root of 4. So there's the y-intercepts. The y-intercept is just cube root of negative 4. For x-intercepts, we want the y value to be 0, so we're going to have 0 equals negative cube root of 8x squared minus 4. Once again, we can look at that and say, well, the only way that that cube root can be 0 is if what's inside of it is 0. We take the 8x squared minus 4, set that equal to 0, which gives us 4 times x minus 2, x squared, minus 2 equals 0. And now in algebra, you probably would not have factored this, but now here in pre-calc, we want to actually factor that as the difference of squares. So we have 4 times x plus the square root of 2 times x minus the square root of 2 equals 0. So does 2 have a square root? Absolutely. What is it? It's the square root of 2. So we can factor that just like we factor the difference of squares, a squared minus b squared, a plus b times a minus b. And that's where we get the x plus square root of 2, x minus square root of 2. So that gives us that x equals square root of 2 or negative square root of 2. Kind of put those backwards there. That's okay. Okay, so take a few minutes and graph and analyze this function.